In the previous video, we proved Warfield's result on finitely presented modules over serial rings, which basically asserts that such modules are serial, namely they have a decomposition into indecomposable modules whose lattices of submodules are uniserial, are chains. So, in general, modules having such nice and manageable decompositions are of importance to us, and much more so are rings admitting that kind of decompositions for all of its modules. Those of you might have seen the videos on pure semi-simplicity problem may remember that if this is a condition on one side of the ring, like if every right module has an indecomposable decomposition, then the ring is what is known as a right pure semisimple ring. If this happens on the right and the left, then this is a property that characterizes a ring having finite representation type. In this video, we are going to look at a particular case of such rings, namely rings of finite type, namely Artinian serial rings, and simply prove Nakayama's theorem that shows that such rings are finite type. And we are also going to show a result prior to the main theorem that shows which of the principal indecomposables are injective modules. Okay. So here are some examples of the Artinian serial rings that are well known. This is the simple Artinian ring. That's the matrix, full matrix ring over a division ring. Upper triangular matrix rings are Artinian serial over fields, and even further they are hereditary, two-sided hereditary. And here's a more prominent and well recognized example: any factor of a PID with respect to a non-zero ideal. So all rings of integers modulo a finite number are Artinian serial. So there are several names alternately used for such rings. Some people choose to call them generalized uniserial. This is a rather old term used for that, and they're also known as Nakayama rings, and equally well-known name for the same kind of ring is Artinian serial, because that's exactly what they are. They are Artinian on both sides and serial on both sides. Now the first proposition is the one that I was mentioning. This is the one that says if R is, that tells us when a principal indecomposable module, namely these EIRs, when such a module is injective over an Artinian serial ring. The proposition says that a principal indecomposable is injective if and only if it is not isomorphic to the Jacobson radical of another principal indecomposable, or ETJ, where J is the Jacobson radical of the ring. Okay. The proof of one direction is quite obvious, because if ERIR is injective, say, and if we assume, contrarily, that it were isomorphic to ETJ for some t, then this would lead to a contradiction, because ETJ is the largest proper submodule of ETR, and it does not split in ETR, which it would have to if it were to be isomorphic to EIR, which we assume to be injective. So that's the contradiction. In the other direction, let's assume that our principal indecomposable EIR is not isomorphic to the Jacobson radical of any of the principal indecomposables, in a given decomposition of the ring. And here's what we're going to do. We are going to use the definition of injectivity, and we will first prove that EIR is injective relative to each of the EKRs, where K is an arbitrary index number in this finite set. So take a submodule or a right ideal inside the EKR and an arbitrary homomorphism from A into our principal indecomposable. Now, remember the fact that in the case of a serial ring, each of the principal indecomposable modules are almost injective relative to each other and including themselves as well. So, for those of you who may not remember its definition, it basically says that for each cyclic module A in EKR, and any map such as this one, either F extends to a complete map between EKR and EIR, or F extends to an isomorphism between a submodule of EKR containing A and EIR. That's the definition of almost injectivity, namely EIR being almost EKR injective. Now, in our assumption, we just wish that F extends to a full map rather than the second condition that defines almost injectivity. Now, A is cyclic because R is Artinian, hence Noetherian, so any uniserial right ideal has to be cyclic. So, because of the almost injectivity relative to EKR, either F extends to a full homomorphism like this, or it is one-to-one and F inverse extends to some map from EIR to EKR. This is the case that is equivalent to the latter condition I mentioned prior to this page. Okay. So if it is the former case, namely this one, there's nothing to prove. But if it is the latter one, namely when F is one-to-one and F inverse extends to such a map, then this map sets an isomorphism between EIR and some term in the composition series of the EKR. And remember, because of the uniseriality and Artinianity, all submodules of EKR are in the form EKJ to the n, where a n ranges from 0 to whatever number. So in this case, we are going to assume that n is greater than or equal to 1. You may ask, what if this n is 0 and EIR is isomorphic to EKR via G? But then G would be an extension of F inverse, which means G inverse would extend F. So in that case, there would be nothing to prove. So we focus on this case, and the situation n equals 1 would be a contradiction to the hypothesis. So we will assume n is greater than or equal to 2. Now, the module EKJ to the n minus 1 is a cyclic uniserial module containing EKJ to the n as a maximal submodule, and it is isomorphic to something of this form. This is because any uniserial module is some homomorphic image of one of the principal indecomposables. So we are assuming that our module ekj to the n minus 1 is isomorphic to the factor of some principal indecomposable, say etr, with respect to some submodule, say b. Now, because of this isomorphism that was assumed, ekj to the n is 0, then this is non-zero as well, which makes b proper. Okay, then under whatever isomorphism this is between them, like this one, the Jacobson radicals correspond, which means the Jacobson radical of ekj to the n minus 1, which is ekj to the n, which in turn is isomorphic to EIR, of course, under our assumption, is then isomorphic to ETJ over B. So now we have this isomorphism. But EIR is a principal indecomposable, so it's projective. Therefore, B has to be a direct summand of ETJ. And since EI is non-zero and ETJ is uniserial, there's only one choice, one possibility, namely that B is 0. Which leads us to a contradiction again to the hypothesis that EIR couldn't be equal to the Jacobson radical of any of the principal indecomposables. So this is a contradiction. So f will extend, in any case, f is going to extend to some map, a full map from EK to R to EIR, which makes EIR injective relative to EKR, and by basic properties of relative injectivity, EIR is injective relative to the direct sum of all the principal indecomposables, which is itself equal to R. But then the Bayer's criterion says, since EIR is injective relative to the ring as a module, then it has to be injective itself, proving our theorem. Okay, now we are going to utilize this nice proposition to prove Nakayama's theorem, which is the main theorem of our video. It says, over an Artinian serial ring, every module is serial. Now the proof of this is divided over two steps, in the first one of which the aim is to prove that any non-zero module over this ring has to contain a cyclic uniserial direct summand. So you take such a module M, non-zero. Now it may be, here's the strategy. In order to utilize the previous proposition, we would normally be looking for a module that is injective and isomorphic to one of the principal indecomposables of R. And the previous proposition says, if I take, for example, one of the principal indecomposables, EIRs, that has largest possible composition length, then it has to be injective. The problem here is that in the case of an arbitrary module, it may just be too much to hope for, to find a copy of such a principal indecomposable inside M. So instead, we pass to the factor ring of R with respect to the annihilator, over which M has the same submodule structure, but it's furthermore faithful, namely its annihilator is 0. So, passing to that ring, we will assume, without loss of generality, that the annihilator of M is 0, now we can search for an injective module inside M with respect to this new simplified R. Okay? So in other words, the injective module we're going to find will not be an injective R module where R is the initial ring that we started out with, but it's going to be an injective R bar module, which now we identify with R by our simplified assumption. Okay? So what you do, because of the annihilator being 0, what we do is this. First you take a local idempotent with the maximal composition length for ER. That means ER has the maximal composition length. There may be more than one such module, but each one of them will be injective. So now our ER is injective. Because of the faithfulness of M, we can find an element like this, which does not get annihilated by the socle of ER. Okay, why do we choose or why do we argue this instead of just searching for an element which is not annihilated by ER? Well, this is obvious because M may not be annihilated by ER, but it could still be annihilated by a proper submodule. In order to make sure that the annihilator of M intersects ER trivially, it is enough for M to satisfy this inequality. Because, well, why are we searching for an M satisfying this? It is because if M is an element satisfying this inequality, and hence this equality, then left multiplication by M on ER will constitute a map, a one-to-one map from ER into capital M. So that in the end, the image of that map, namely M times ER, will be the injective R module inside capital M that we were looking for. So that's the idea. Now, having said that, once you get your M satisfying this inequality, we are done. We will have found the desired M. So that gives us a cyclic uniserial and non-zero direct summand that's isomorphic to ER inside M, proving the first step. Now in the step 2, we will follow the classical method of decomposing a module into indecomposables and take a so-called maximal local summand, namely this UI, this family of UIs, consisting of uniserial direct summands of N. What this means is that when I said local summand, that's what I'm trying to explain. What do we mean by local summand? It means that any finite subsum of these UIs is a direct summand of M. And furthermore, these UIs are uniserial, cyclic, and non-zero. So you can choose by Zornsdam a maximal such family and take the direct sum of it, call it U. And here's what we do. If U is not equal to N, then N over U, the factor module, is non-zero. Then by step number 1, it contains a cyclic uniserial direct summand such as A over U, which is complemented in direct sum by sum B over U to N over U. Okay? And what we have is a cyclic uniserial direct summand of n over u. Okay. Now, since R is Artinian and A over U is cyclic, A over U is finitely presented. Why is that? Because Artinian rings are Noetherian, and every cyclic or finitely generated module is finitely presented. Namely, a finitely generated projective module factored with respect to a finitely generated submodule. So, it is well known that finitely presented modules are so-called pure projective modules, which means they are projective with respect to any pure sequence. So where is the pure sequence here? Well, look at this U. U is basically, U can be viewed as the direct limit of the some pure submodules of n via inclusions, and these pure submodules are basically the direct summands formed by taking finite direct sums of the ui's. So in other words, U is the direct limit of finite subsums of ui's. Okay? That's why U is a pure submodule of n, and hence of A, which implies that this projection with kernel U has to split, because any pure epimorphism onto a pure projective module is a split epimorphism. So U is a direct summand of A. So let's say it's a direct summand of A via some complement A prime, which has to be isomorphic to U over, did I say it right? Yeah. A over U, which has to be isomorphic to A over U, which is cyclic and uniserial. Now, since it's cyclic uniserial, here's the situation. Okay, since U splits in A via A prime, then A is the direct sum of A prime and U. From here you can easily see that B direct sum A prime is n. And then remember that U is still inside B, which means the family, if you adjoin the uniserial module, the cyclic uniserial direct summand A prime, to the family ui's, then this will be a family that contradicts the maximality of ui's as described. It's easy to see. Right. Okay, so which is why U has to be equal to n to avoid that contradiction. Namely, A over n over U has to be 0. Okay. So this proves the theorem. Now we have the corollary that we want. An Artinian serial ring has finite representation type, because you see every indecomposable module over this ring is a uniserial, and this means it's isomorphic to a factor of one of the principal indecomposables, which comes in this form. But for each principal indecomposable, there are only finitely such factors, and there are only finitely many principal indecomposables, which means the number of possibilities for the isomorphism classes of such modules as I've just encircled is finite. So now, along with Artinianity, this implies finite representation type. So this yields the result. Well, that proves what we've been trying to do. Hopefully, in the next video, we will continue these discussions and present to you some other hopefully interesting and prominent results on serial rings. Goodbye.